So good to see all of you again. If you're new, welcome to our bi-weekly vLLM office hours. My name is Sasha Zelenovic, and I'm a product marketing manager at Red Hat. We've been putting these office hours together for nearly a year. We started last June, so we're coming onto our year. This is our 25th session. We're super excited. If you ever want to check out previous sessions, we have all the videos and slides on our registration page. Just scroll a little bit down and you'll be able to see them. It's been a super busy week for vLLM. We're just fresh off a New York City meetup last night that actually went great. We had a lot of fun sessions, and we'll actually be bringing some of the sessions to office hours over the coming weeks, including the Torch that Compile session that was given by Meta and our team at Red Hat. So that's coming in the near future. So I'm here with my co-host, per usual, Michael Goin. Michael is a principal software engineer at Red Hat, also a vLLM committer from the early days. And we're also joined by Red Hat's Russell Bryant, a distinguished engineer and also a vLLM committer. So we are in great hands today with two vLLM committers. We'll be giving you an update on the most recent vLLM release. Michael will do that, and we'll pass it over to Russell to talk about structured outputs in vLLM. So, Michael, if you can please go on the next slide. So please join the discussion, guys. Ask questions. Feel free to unmute. Seems like we have a little bit more of an intimate session today, so don't hesitate to speak up. We will be live streaming the session right now when Michael kicks off, so you can find the recording pretty much immediately on our YouTube channel. So we'll also post it on X. Feel free to reach out to us if you have any questions after the session. You can also find all of us in the vLLM developer Slack. Michael, I'm not sure if you shared the presentation yet, so people can get the links.
Yeah, I'll send my message.
Yeah, that's great. Thank you so much. While you're doing that, you can just click. Yeah, well, Max, nice to see the Brazil flag up front. I was gonna make a joke, it's alphabetical, but that wouldn't work. But the honest thing, Max, is probably because you're the most honored or the most attended attendee here. You've been to probably the most sessions, and you always used to, say Brazil. So here it is. So yes, are there any, well, since Max mentioned that, are there any people here that are from a country that is not listed on the bottom right corner? Yes, hello from New York City, Michael. Um, it's been tough lately because I feel like we're exhausting this. Maybe it's time that we open the office hours to a more global audience with different time zones. San Francisco, nice. Santa Cruz, California, I love it. Who else do we have? Rio, Brazil. Oh, nice, Wallace. That's great. We have a couple of Brazilians. Hey, Vermont, USA, great. I'm in Massachusetts, I believe. Russell is in South Carolina, San Francisco. Anyways, thanks everyone. Thanks for being here and supporting this program. I'll pass it over to Michael now.
Yeah, thanks, Sasha. Hi, everyone. Michael here. Today we're going to go over, a project update with quite a few new things in vLLM 0.8.5. Actually, the model list here is not quite right, although Qwen 3 did come out during the release, and we had a little bit of tuning for that. But there were a lot of improvements for multimodal models, bug fixes, and various model supports that we'll quickly cover. Of course, our guest topic today is structured outputs in vLLM. First, how they work, what are structured outputs, and then, how vLLM is actually architected to implement it much more efficiently than we've implemented it in the V0 backend, which should be pretty cool to dive into the performance of. As a reminder, our next office hours will be a deep dive in Torch Compile and its road to performance in vLLM. That'll be co-presented by Luca from Red Hat and Richard from Meta, who have worked a lot on this and yeah, have a lot of really cool things to show as well. So to kick us off, let's talk about vLLM. If you aren't familiar with it by now, it's the fastest growing standard in open source model serving. That's because it's pretty fast and easy to use. And of course, it's very permissively licensed and has a lot of different contributors from industry and academia. It supports hundreds of different model architectures, has a very close integration with Hugging Face transformers, As I mentioned, research and inference acceleration. Very often, papers fork vLLM and make their paper about some new innovation they made on top of that, and very commonly those forks end up as PRs, and we integrate these and keep moving on to better and better performance. So it's a very diverse community, and of course, with diverse software, there's also diverse hardware backends. So in addition to getting yeah, good performance on NVIDIA GPUs. There's also support for AMD GPUs, Google TPUs, AWS Neuron, Intel hardware accelerators, Huawei Ascend, and even CPUs. And then along with all of that, hardware flexibility, we bring a lot of different inference features. So we're not just talking about serving, text-only large language models. We also serve, multimodal models, multimodal inputs, and recently some multimodal outputs. Embedding encoder-only models, reward and re-ranking models. So you can start. So vLLM is used in like RLHF workflows as well, and inference scaling workloads. And then, of course, optimization techniques for faster model forward passes like quantization or custom kernels written in Cutlass, Triton, or obviously with Torch Compile, as I already mentioned. And then, inference system level optimizations that are for more effectively scheduling work to run on the LLM, like chunk prefill, prefix caching, multi-LoRa, batch serving, speculative decoding, disaggregated prefill decode, lots of tools and tricks there. And then application level features like tool calling and structured outputs, which of course Russell will go over today, and many different types of parallelism so you can run models performantly across more than just one hardware accelerator, splitting up models with, tensor, pipeline, expert, and data parallelism. So obviously a toolkit full of a lot of things and, of course, an ever-growing list of flags, but also, we work really hard to try and make the default behavior get better over time. Um, so yeah, that's what vLLM is. What Red Hat is, since both myself, well, Sasha and Russell are all at Red Hat now. We're a top commercial contributor to vLLM, and we help enterprises scale their deployments of vLLM as they choose it to build their inference infrastructure on. We worked a lot on optimization, so some of those custom inference kernels, a lot of the quantization integration, Torch compile trying to turn those like simple declarative PyTorch-based model definitions that are very close to Hugging Face transformers, but actually start to get graph compilation and really advanced performance engineering and custom op fusion. That's been a great infrastructure for that. And then also reducing a lot of system overhead, reducing CPU overhead, re-architecting things. We worked a lot on vLLM v1 and trying to improve the default performance of vLLM and reduce the overheads that v0 faced. And then of course production features, things that enterprises use all the time, like metrics and dashboards and uh, integrations for new application features like structured output tool calling and of course the new models of the day. Yeah, if you want to work on vLLM, we're hiring. That's our plug. And of course, we use vLLM in a lot of our different products at Red Hat. And like I said already, enterprises want to run a variety of models across a variety of hardwares, across a variety of locations, and vLLM is core to our products to help enterprises scale their deployments. So I wanted to call out, before we move to the vLLM update, I want to call out some new blogs that are probably relevant for this audience. A really big one, vLLM was part of the CNCF or the Linux Foundation, but we actually moved to the PyTorch Foundation, which is newly found by the PyTorch group. Both vLLM and DeepSpeed joined this week, and we will collaborate even closer with the PyTorch team to further feature development. This also means, vLLM is run in like the Torch nightly CI. So, we'll get better support with PyTorch as new releases of PyTorch come out. And overall, Meta and the PyTorch team have really recognized vLLM as a crucial consumer and co-developer with PyTorch. So we're really excited about that recognition. And then another thing is a really cool blog from Snowflake on some speculative decoding methods that they built on top of vLLM with Arctic inference. If you're interested in speculative decoding, I highly recommend reading it. It combines suffix decoding with custom like LSTM, MLP speculator models. It's a pretty cool blend of old and new ideas. And it's implemented as a plugin in vLLM, and they open source the repo. So it's really easy to get started and play with it as a plugin into vLLM if you're interested in seeing if that could optimize your workflows. It's especially good at coding workloads. So, without further ado, I'll get into what's new in the latest release of vLLM while the last 2 weeks have passed. This is a pretty big one. There's over 310 commits from almost 150 contributors, and 55 of those were new contributors. So we are, yeah, dealing with a lot of activity in the project, which is really great. As I mentioned before, there were a lot of pretty important like multimodal bug fixes and performance issues that have been resolved. Overall, we're trying to improve the throughput performance or offline performance of multimodal processing. And there's some kind of bottlenecks that we identified on the front end or like input pre-processing for multimodal items. And we're yeah, working on that specifically as a performance item. Of course, Qwen 3 came out within the past 2 weeks, and we had day zero support for that. That felt great. And then we also landed for structured outputs, a new structured tag feature to allow for structured outputs inside of tool calling, which is pretty cool, and Russ will probably talk about a bit. Lots of new models added: Modern BERT, Kimi VL, Qwen 2.5 Omni. Although just the thinker side, we haven't added the multimodal output yet. But a good start towards more multimodal outputs. And then some more work on Llama 4, tuning that, particularly AMD performance. I wanted to call out like one breaking change. If you were disabling chunked prefill manually or disabling some of these other arguments like multi-step stream outputs, we changed these to not be like Boolean args and more be like no PR args, just to be more consistent in trying to equalize all the different arguments we have and try to set some standards there. So beware if you upgrade. Yeah, with respect to, of course, working in the V1 engine, there's still a lot more support things that we're porting either from V0 to V1 or adding in new development. One of the big things is we're working a lot on disaggregated serving, so disaggregating prefill and decode. We introduced KV connectors and the LM cache integration in V1. And we're adding quite a few new ones, like a Nixel connector, which is pretty exciting. And we'll have more to share about that at the next office hours. Yeah, just some general like optimizations for MLA. I landed Flash Infer attention in V1, which is pretty great. I'm excited about that. That should look forward to some nice improvements to Flash Infer over the next few weeks. Wink, wink. Um, we had some optimizations for like incremental detokenization. Detokenization. This actually comes from the Hugging Face tokenizer library, adding a specific interface for this, so we no longer need to do a kind of hacky thing of manually keeping a running track of tokens and tokenizing, detokenizing these together to handle efficient streaming. And then a really big thing that we've been pushing on is Eagle 3 support. That's basically, the state of the art in terms of speculator, speculative decoding performance for speculators that you train. So we've implemented that, and now we're starting to really tune and optimize for that, and also start training some Eagle 3 models to plug into it. Another thing that I want to point out is we've expanded the audio from the transcriptions endpoint to finally support sampling params, so it's not just stuck at temperature 0. Greedy decoding, and yeah, the dynamic loading LoRa's from a remote location has been a requested feature for some big workloads for a while, so we're happy to get that in. And then we're working on finally making some of the benchmark scripts not in a benchmark directory that you need to clone vLLM to run, but rather putting them in the CLI. So just like you can do vLLM serve, you can do vLLM bench. So these are still a bit early, but I worked on these a bit and try them out, report issues, but they should basically be the same, benchmark latency, benchmark throughput scripts that you see in the existing, benchmarks directory. And we're hoping to move more of those internal to the package for, easy use. Some things on performance. There's been a good bit of optimization on Flash Attention 3, as this is still the default attention backend we use in V1, and particularly for Hopper GPUs. We also have added an MLA backend for Blackwell GPUs, so we can enable, running DeepSeek efficiently on, B200s, GB200s. And similarly for MOEs, we're adding a fused MOE Cutlass backend for Blackwell GPUs with the expert map support. And another quantization library landed, this BitBloss library from a Microsoft team. That's pretty cool. Builds on top of TVM and is going to lead to bitnet support in vLLM. If you've heard about that from Microsoft, the like 1.5 bit precision models, which I'm pretty excited about. Yeah, there were some security updates. Russell also works on security, so if you have questions about that, definitely give him a ping. He's been working on a lot of CVEs from the project, so we're very thankful for that. On the hardware side, there's been a good chunk of work on TPU and V1, enabling more features and improving some performance for multimodal models. On AMD, they've been pushing a lot of new kernels and performance with their new Aider kernel library. Um, and also just doing various optimizations for bottlenecks as they come up, particularly for attention, as the V1 attention backend for AMD is still pretty new in tuning it, but yeah, it's progressing pretty well. And yeah, some various documentation, examples, guides. Continuing, we're always trying to improve documentation. Let us know if there's something that's not clear to you. There's a lot more work we can do here, and it's, yeah, best if you let us know what you care about. So that's all I wanted to cover. And now I'm gonna hand it off to Russell to give us a whirlwind tour through structured outputs.
Thank you, Michael. I'm gonna steal the screen. So one moment. All right, did that work all right?
Yeah, look good.
Fantastic. So yeah, I'm Russell Bryan. Thanks for having me on. I'm going to talk about structured output support in vLLM. It's something that I spent some of my time this year working on, and I find it's really fun to work on, really interesting. So excited to share with you. Michael said earlier that this is an application level feature. So I'm going to start from a user perspective. So maybe if you haven't used it, or maybe you've only used it a little bit, I want to start with what does this mean for a user? What can it actually do? And how you would use it as a user. And then we'll start going down from there and then start to look at like what's a mental model for how it works, not the Python code yet, just thinking about how a model works, where does this fit into the sort of the big picture? And then I'll give you pointers to where it lives in the code base, and then we'll dive into some performance results, which I think are quite exciting for the latest version of this feature in vLLM. And everything is roughly, as of 0.85, as Michael talked, he talked about that as the latest release. So that's what this reflects. The features change all the time. So in a month, we'll probably have additional things. But here we are. So starting from the user perspective, what's the over the feature, and then what are the key options you should be aware of? Right, from the top level, what does it do? It lets you constrain the output. So sometimes you want to put constraints on it. You can think about it as like the model output format police, right? So especially when you're writing code that is interpreting the output of the model, it's really helpful to be able to constrain it so you can have, enforce your expectations on what that output's going to look like. And you can make use of this feature pretty easily, both through the Python API and the OpenAI compatible API server. So let's dive in. I'm going to go through like the different ways that you can use the feature, the different ways you can express your output constraints. And the first one is a set of choices. So take, for example, this is good for classification type of a use case, maybe asking yes or no questions, or in my sample here, we want to choose a color, red, blue, or green. And so what you really want is literally the word red, blue, or green, right? So if you're not using this feature, what you might get is something where, okay, the model's getting wordy and philosophical, and wants to tell you it doesn't perceive color, but let's go with green. And that's not helpful, right? That's actually kind of frustrating. You wrote your code to expect a color, and it gave you a lot more than that. You just wanted the word green. So what are you going to do? You use this feature, right? And like if this is what it would look like in the Python API, you're going to give it an array of these three things. And that's all you got to do. And you're expressing your constraint on the output to be one of these three strings. All right. Oh, cool. Now it's going to give you green. And how does that make you feel? Now you're much happier, right? So that's the feature. Less headache, more happy. Um, Another example, JSON output. So again, thinking about the case where you're writing code that's interpreting results, it's super convenient to have a structure, especially when the data you're getting back might start to be more complex. Having it in an easily parsable format like JSON is super convenient, and we can enforce that to be true. So what you can do is you specify your expectations in the form of a JSON schema. Okay, and then we will enforce the output to follow that schema. So just as a simple example, generate a JSON object with the keys, a name as a string, an age as an integer, and a Boolean as is student. Okay, so what might happen if you don't use structured output, but you told it on a JSON object, this is close. Like on the first hand, it looks like it might be right, but comments are not valid in JSON. So while it looks like the model got so close, you get a parse error and you're not feeling good again, and you're irritated. So what you want to do is you specify, what we have in the prompt here. That's an object with these three properties. You specify that as a schema, and you actually get proper parsable JSON now. And you're feeling good again. Okay, so you get the pattern. So we'll go to a third example. Another format you can use is regular expressions. For example, if you want a date in this format, 4 digits for a year, 2 digits for a month, 2 digits for a date, and you can specify that in regular expression format. I won't go through like the whole thing of what happens when it doesn't work right and what happens when it does, but we'll jump ahead to how do you feel after using this one successfully? Trick question. You still have a headache. But that's because regular expressions can be quite frustrating, or they or they can be for me if you've ever spent a bunch of time debugging complex ones. Um, and now I'm going to take you on a little bit of a side journey, because this is what happened to me while making the slides. I went on a sidetrack. So I was like, oh, I wonder where do we use regular expressions in the code base? So I searched, and I pulled 3 out of the code base. So these are actual regex from the repository necessarily. So if you have a lot of time and you like regular expressions, or even if you don't, two side quests for you. One is take a look at these and figure out what they do without finding them in the code first, and see if you can figure them out. Or as a second quest, you can go find where that first one is used in the code, the shorter, simpler one, and come up with a case that breaks it, because I thought of one when I was reading the code. So anyways, that's regular expressions. They're powerful and sometimes frustrating. Okay, moving on though. Another example of the format you can use, you can express a grammar. So depending on the backend you're using for structured output in vLLM, there's different types of grammars you can support. So you should look into that in a little bit more detail. This is an example from one of our example scripts that we have in our documentation, that just trying to help demonstrate it. A grammar that defines a trivial SQL query. But you can express your constraints in this type of format. And then lastly, this is a new feature. It's probably the most complex one that we support, and it's new in the latest release. It's called structural tag support. But I talked about, if we go back a little bit, I talked about JSON schema, where you can define a JSON schema to express that as your output format. What this lets you do is specify a JSON schema, but have it only enforced on a subset of the response. So imagine it's sort of like free-form text in the response, but at some point, you want to start enforcing the format somewhere in the middle, and then go back to letting it be sort of free again. And a key, the key use case for this is tool calling, where in the middle of the response, the model's generating a tool call. When you hit that point, we want to enforce it to make sure that that tool call is valid and fits the formats that we expect. So that's what that's going to let you do. You can expect expansions to this coming in the very near future to add even more flexibility to how this could be specified. And then also probably us on the development side, making more automatic use of this sort of thing to improve our tool calling support. So that's some of the work to look ahead to. So those are a lot of the formats. If you wanted to use this, what I'd really point you to is our documentation website. We've got several examples of both using it on the OpenAI compatible API server, but also the Python API, and had what just trivial examples of using the different formats in both cases. So that's where you should go. But it's really it's adding a single extra field to the request body on the API server side. If you're using Python, it's part of sampling params, or a subfield in there is the guiding decoding parameters, which is another name we use sort of interchangeably about the feature. And then in there, put your schema or whatever the format is that you're specifying. So that is structured output from a user perspective. So now I wanted to walk you through like the mental model that I use for just thinking about the feature from the highest level. Just how does it, what part of the process does this operate in, so that you should have this kind of in your mind before you start looking at the code, because it kind of gives you an expectation or maybe some instincts about what you're going to find when you go look at implementation. But I'm going to start like the highest. We're going way back here. So trivial example of an LLM, and I'm going to assume words or tokens for the purpose of the exercise. Simple yes no question, right? Is vLLM fast? Maybe the output is very. Remember, but I really wanted yes or no. But that's the question. Now, if we look just a little bit closer, what the model is actually producing is a set of probabilities for what that next token is going to be. And then we have a sampling phase that happens there at the end that chooses the token, right? So given these probabilities, we're going to choose a token that's going to be that next one. And so, given my trivial example of is vLLM fast, and this model decided very was the most likely thing, and so we chose it. So here's where structured output can come in. So if we want to ask that question, but say the only valid answers are the words yes or no, then this is where structured output comes in. We get those probabilities out of the model, and then we start masking out the ones that are invalid. Right. So when it comes to that sampling phase where we go to actually choose what the next token is or what the next word is in this sort of conceptual example, we've erased the everything else that's not valid from even being in contention to be chosen. And so here, since we eliminated very, now we chose yes instead. So that's conceptually where it fits in. And if we look a little bit closer, thinking about what's the data flow, what kind of information do we need to keep track of? As these token predictions are coming out and going into our sampling phase, at that point, we've got something that's keeping track of the structured outputs and what's currently valid based on what's already happened, and then it's going in and applying those constraints. Once in our sampling, we've chosen that token, that needs to be fed back in. So, you can imagine there's this component that as tokens are coming through, it has to keep track. It's sort of changing its view on what's valid to come next. If you think about a JSON object, when a curly brace is valid, or when a quotation mark is valid, or a comma, these things are different depending on what's come before it. And so that's what the state tracking is going on. And at each phase, it's sort of enforcing a new set of masks, or a new mask on what the valid next tokens are. So that's the conceptual model for how the feature works and sort of where it fits into the process of running a model. So in vLLM, where would you find the integration? Here's some pointers if you want to dive into the Python code. So one is the structured output directory under V1. That's most of the code in there is backend integration. I haven't really talked about the backends too much, but we owe quite a bit to the authors of the backend libraries we use, in particular XGrammar and LL Guidance, are the two libraries we're using right now in V1. There's also a PR up to add outlines core support, but these are the ones that are doing the really hard work of you've expressed your constraints in one of these formats, and it's compiling it into some internal representation, and and doing the state tracking and generating what those masks are on a per token basis. That's all driven by these backend libraries that we've integrated with. And so you can find the integration with each of those libraries in there. There's a engine processor file that's input validation. So like when this request comes in and you've specified a JSON schema, is that JSON schema is that even valid? We'll catch that early on in the request, and it'll generate an error. So we do some validation in there. There's also the scheduler. That's where some of the trickier integration. That's where we do a lot of the state tracking when as new tokens are generated. We have to update our state, and then before choosing a token, we're generating these bit masks that are used to ensure that we pick a valid token. A lot of that is integrated into the scheduler code. And then there's the model runner backend, so kind of per accelerator type. And in V1, both the GPU and TPU model runners implementations have support for this. So if you go in there, you'll see the sort of hardware specific code where it's taking these bit masks that reflect what set of, which tokens are valid to be chosen next and how it actually applies it. Yeah, so that's where you'll find it. Okay, so this part was maybe the most fun I had. Probably the most fun I had preparing for this is going through and seeing how fast it is, and generating some comparisons, and even getting some new insights that I hadn't trying some new knobs I hadn't tried before. So this is as of this version string, which is roughly after the last release, but before we haven't tagged 0.9 yet, but it was like main as of Monday or something like that. All right. So one thing before we get into the specific numbers, like what are the different trade-offs here that are going to be reflected in results? One of the key things, at least, so I am by no means like a deep expert on how these backend libraries work. The folks that work on those are very approachable and nice, and if you jump on our structured output channel on the vLLM Slack, they're there and great to chat with, and could talk to some more details. They also have good information in their GitHub repos and so forth. But one of the key design choices is how much processing or initialization you're going to do up front at the very beginning of the request, given this schema or grammar, versus how much are you going to sort of do on a per token basis. So that's one of the trade-offs that's different between those two backends, and we'll see a little bit of that in the results, how that trade-off plays out. The functionality changes on a pretty regular basis on which of these, which features are supported in each backend. So for example, JSON schema has lots of different options in there. Not all backends support all the options at a given time. I actually pushed a pull request within an hour of getting on here, probably, to enable 2 more properties with XGrammar. Just for was it just coincidence? So this stuff changes. So sometimes you got to check or test, and you'll find out that might help make your decision for you. And then with XGrammar in particular, there's some knobs that we kind of play with. There's caching that goes on. We have this on by default. You usually don't need to think about it. You can change the cache size. The default cache of just 512 megabytes is roughly enough for caching about 1,000 JSON schemas. And so that's probably enough for most cases, but that's a knob. And the other one that I was, this week's first time I actually started tweaking it was the thread pool size, and to see how that may help. That was on recommendation of the library author when I was sharing results with him. So that's something a little bit more work for us to do to make that, expose that as a knob that you can tune to get the best performance depending on your use case. Another thing is if you tried this feature in the past back with the V0 engine, one thing I hope you take away from this is that you should try it again. We know that the performance in V0 was not ideal when you turn this feature on. Just one structured output request had a significant impact on the whole system's performance. This is a chart from an actual production system. And they're just pointing out how the impact to the entire system when structured output requests came in. So that's something we know, but it's gotten a lot better. All right, test number one. So I ran a set of requests, some without using any structured output requests, just as a baseline to compare against, and then using XGrammar and using guidance. When it's on, I sent 100% of requests were structured output, just to sort of really highlight what the performance impact might be. The data set I used in our benchmark scripts refers to it as XGrammar bench, but it's a data set of JSON schemas that have a lot of variety in the features that are there. We use like less than 100 schemas from this, and so since it's a relatively small set, it's going to benefit from caching in XGrammar. And I ran several scenarios based on the number of queries per second, from 1 up to 25 over about 90 seconds. And there was a maximum output length enforced of 300. So what are the first results? So this one shows V0 against V1 at different QPS levels. And as you might notice, there's really only one bar you can see, and that's the V0 bar. So it's drowning out the results. So next we'll zoom in down here on the 1 and 5 QPS and see if we could maybe see something, since you can't even see V0 there. All right, so now we start to see the V1 results there at the bottom, the blue, red, and yellow, but still the V0 results are still making it hard to make much sense of the V1 results. So this is the last I'll show anything about V0 performance, again, just to make the point of, hey, it's a lot faster now. But here we go. This is only the V1 engine. And so the takeaway here, so what this chart shows is this is the mean teapot, or time per output token. So as generation is happening, every single, what's the mean time in between each output token that's generated. And so that the first bar there is without using any structured output with the requests, and the other two is the two backends. And so first takeaway, very, very little overhead on a per token basis in this case. And there's a very, very slight edge with XGrammar over guidance, and that's likely due to the caching that we get from XGrammar. So that's one thing. Time to first token. So this is the latency. So how much time from sending a request to when that first token is generated and you get it back. There's a little bit more you see here. That's not necessarily surprising. There's some initialization we have to do up front. Yeah, so that's what we see here. XGrammar is fast, shows a little bit faster time to first token. Again, this is because of the caching. Oh, actually, this is the big impact from XGrammar's caching is the time to first token. I'm going to back up a second. The reason that you see guidance being slightly higher is it's doing more work on a per token basis. So it's a little bit higher here, but it's doing. Yeah. Okay. Moving on. Test number 2. The main difference in this test was I used a different data set. This is JSON unique. And so this is a little bit of a worst case test where every single schema, every single request has a JSON schema that's unique. It has, so we start with a schema that has 10 fields in it. And then in the code, we're like adding a unique field every time with like a UUID based name. And that's just to force it to be unique, ensure that we're not getting any benefits from caching effectively. Okay. So I did XGrammar twice because this is where I got a recommendation to try seeing how what the thread pool might help with, what that might do. So by increasing the number of threads, we cut the time to first token roughly in half for XGrammar, but it's still obviously takes much, it's still taking, well, relatively quite a bit longer than guidance, because it's doing a lot of its initial, a lot of processing up front versus on a per token basis. So in this most extreme case, you can see how that trade-off plays out. the requests with XGRAM are taking a little bit longer. And then time per output token, the with the larger thread pool size, we actually got a bit of a hit here. And I think it's because I had the thread pool size too high. It actually started making things worse. And so after further testing after this, found a sweet spot that was lower. But again, this is visible in a pretty extreme case, and we hope that the defaults really are actually good for most of the case. But some takeaways I take from this. First of all, the default backend setting we call auto, and hopefully that's good enough for most people, and you don't really have to think too much about which backend is being used. And we call it auto because it's sort of will adjust the behavior over time. It depends on which features are supported in each backend at a given point, or different things we learn about performance characteristics on a given request. Then we will choose which one to use, given the best choice we can make in the code at the time. With XGrammar, since it's doing more of the work up front, I think it shines on if you have really long generations, the benefits you can get on a per output token basis, I think are that it shines there. With guidance, the really fast time to first token, no matter how complex your grammar is, I think it really shines there. So if you're in a case where maybe it's a multi-tenant environment and you've got lots of different applications throwing incredibly complex JSON schemas at you, and you can't even predict what they're going to be, this might give you more predictable performance. And so that's where that one I think shines. But honestly, they're both incredibly fast, and I had to give it a pretty extreme case to be able to show to show some differentiation. Some future work. So the biggest thing that's and this is in an open PR at the moment, is jump decoding. And this is a really, I think, it's a clever technique, clever optimization. So, again, since you've specified constraints on the output, it's possible that once a certain token is chosen, that we know what the next token or next set of tokens have to be without even using the model. Like we can just jump ahead. That's the jump part. So let's say you specified your output must be, it's following this JSON schema. It's a JSON object, and it's going to have and you require these 3 properties to be in the result. So if the first token, is an open curly brace, we know that the next one has to be a quotation mark. Like there's just we don't need to run. We don't need to use GPU time to figure that out. So there's just parts in the output where we can jump ahead because there's no other choice but for the next tokens to be some set of them. And so that's an optimization we're getting integrated. The libraries have great support for this already. Just a matter of kind of getting it all hooked up just right. And one of the tricky things with a lot of these features, with structured output in general and optimizations in general for this and other things, is making sure that they work along with everything else that vLLM does. That's like one of the challenges. That was one of the many design goals in V1, was to try to make sure all these features and optimizations work together. So that's like, one of the tricky things we're making sure we get right there. I mentioned this a little bit, just expanding our integration and support for tool calling, reasoning output. There's just these other things where this feature can be utilized to improve vLLM. Then this back end, using the outlines core library, that's up for review. That shouldn't be too much longer. I'm sure there'll be more, but that's the sort of things on top of mind for me. And that brings me to the end. That's everything I had today. So I think I will turn it back over to Sasha, Michael, to see take it from here.
Yeah, thanks a lot, Russell. Really appreciate that, especially diving into the benchmarks. It's always a task to try and understand benchmarks and rationalize them and have good takeaways. So yeah, do folks have questions up at front on anything today?
I don't have any like obvious questions other than like good work. That is excellent. That's all I gotta say.
Cool. Well, if you give it a try, if you have any feedback based on things that work well, don't work well. Would really love to hear it, because that's how we can make it better, is make sure we're working off of what the real experience people have. If people are really interested in this feature, I'd encourage you to join we have a Slack channel that's sort of dedicated to the feature in the vLLM Slack that you're welcome to join and talk about what we can do to make it better.
Yeah, okay. I'll give it a shot, because I think I'm still on V0 for now. I haven't noticed too much difficulty with the structured output stuff right now, but I am very interested in the structural tags that you guys had, because that's been like a thing I've been trying to get in outlines for a long time now. And so I'm happy to see that you guys have availability for that. So.
Cool. Yeah, there's going to be a pretty big expansion of that coming in the next say month or so, just in terms of adding a lot more flexibility there. So I think, yeah, it is certainly the most exciting thing happening in terms of the options we have for expressing your requirements.
Does it support like repeated blocks of like triggered stuff? So for example, if I have like markdown blocks where it's backtick, backtick, backtick Python, then I would apply like a CFG within there.
Yeah, so in the way does it support that? Yeah, so like there's a thing that there's triggers at the bottom, and that's like the thing that triggers turning it on. And so like, let's say a trigger could be 3 backticks. You could express that, and then once that happens, you can express then the structures thing above is once one of the triggers happens, what are the different you can specify multiple structures, but like maybe begin might be triple backtick and then the word Python, right? And then here though, your only option for the body of this is a JSON schema. That's kind of one of the things I'm referring to, is that there's going to be an expansion of the flexibility here. So maybe not just
Right.
JSON schema, but maybe within this, we're going to enforce something a little different. So
yeah,
I think
like
there's
regular expressions and stuff.
Yeah, so we'll see where we can take it, but right now, the inside, once you flip once the switch gets flipped on, it's something at the beginning, something at the end, and then JSON schema enforced output in the middle is what's there in the first cut.
So can you tell me the distinction between triggers and begin? They seem
Yeah,
like
so
pseudo redundant.
yeah, a little bit. So in this case, the function calling, in function calling, let's say you have like a bunch of different functions. So the trigger is like sort of a unique, no, not UT. It's like one thing that turns it on, but then you have function get weather, function get calendar. I don't know. So we definitely could use like this might be like the only example. I think this is the example I use when working on the integration. But definitely we could it would be good to expand documentation to show more complex examples and more varied examples to make this more clear.
Okay, cool.
Yeah.
Thank you.
Sure.
I guess I can quickly chime in. So basically the difference between triggers and begin here is that essentially triggers will allow Xgramma to know when to start applying the bit mask. So because this is like a specific Llama 3 function calling schemas, right? So essentially when it generates this section, right? When it first see these tokens, it will know that like it should start applying the bit mask for this specific structures. And then once, it reached the end tokens, and then the model can freely generate after this end tokens. So that's the only difference. That's all. Yeah.
Great. Thanks, Aaron. And Aaron's another vLLM developer who has also worked on structured output support. So thanks for chiming in, Aaron.
Yeah, oh, sorry, there's someone with their hand up. Douglas?
Hey, how's it going? Awesome presentation, thanks. And I gave it a whirl while you were talking, which is awesome, and it totally worked right out of the box. So you showed that diagram where it actually happens, where it kind of like goes into that loop where it's I guess checking against the the structured output rules that you've got. Now, just to use like a ridiculous example, if I have like a rule set that has like something that would like really influence it, like saying begin in your last example, and then you put the sky is red like 45 times or something like that. That is gonna wind up influencing the output, right? Because it's sort of like it's like trying that until it gets that content and it's part of the context. Does that make any sense at all?
Yeah, so you're thinking about how like by using this, it's sort of like you're sort of forcing or impacting the context and then impacting what comes later. Is that kind of what you're thinking through?
Yeah, exactly.
Yeah, I mean, I think that's like, yeah, I mean, that's pretty much it by design.
Okay.
Like if your requirements are you require it to follow these rules, then it's going to go that way, and we don't give it any other choice. And that certainly will change what you're going to get versus what you would have gotten if we were hands off and just let it do its thing.
Which absolutely sounds like the right outcome. So okay, cool. I got it then. So thank you. Yeah, that's awesome. Thank you. Appreciate it.
Yeah, thanks.
Yeah, maybe one thing, since it kind of came up with like custom logic processors, for a bit of like history in V0, structured outputs were sort of implemented as a custom logic processor. However, in V1 we wanted to separate this. Um, yeah, Russell, maybe if you could like talk about some of the reasoning behind like treating these separate.
Yeah, so if you go back a slide, I think, just to make sure that people are on the, yeah, this one, just to make sure people are on the same page about when we say custom logics processors. So output of the model, set of probabilities, what the next token is going to be. That's the logics, okay? So this is like we have a bunch of, probabilities associated with tokens. Custom logics processors, this is, you want to write something that's going to process those and modify them in some way. You want to add some sort of um, bias towards some certain tokens, or you want to add some penalty. I don't know, whatever you want to do. That's kind of the block where we put it in is we can run your code and let you modify these things. And you can see that structured output, that's exactly what it does. It's modifying these things, modifying the logics. Now, in V1, again, so back up a second. One of the goals about V1 is we want to make sure all these features work well together. And so we have to think carefully about what every feature does and where we put each part of it. Structured output is not only that. And so we're thinking ahead. It's not just processing the logic. It's also, say, jump decoding is a good example of this, where there's actually more going on than only processing logics. We may actually be generating extra tokens or emitting extra tokens to skip running the model to do that. So it's a little bit more than just that. So now we're treating it as its own special feature where we account for the things that are unique to structured output, and so that's why we did it that way. Custom logic processors will still be a thing. I think Michael put in the chat like that it's a work in progress and linked to relevant issues or PRs. Oh, we still allow it, but it's just different. So it just became clear that putting it in that box was too limiting for what we wanted to be able to do with the feature going forward.
Yeah, definitely. So it's kind of been elevated into the scheduler,
Yeah.
and is kind of like speculative decoding where it can start to do fancier things in the future.
Yep, Aaron's been working on the jump decoding thing, by the way. So shout out to Aaron for working on that. That'll be great when we get that done.
Yeah. Are there other questions? I'm trying to understand this agent one.
Um, I haven't followed the chat, so
Yeah, yeah. It's just a bit of a
I see.
Can
Yeah,
I can ask the question and maybe like I wasn't very clear in my question. Do you guys hear me by the way? This is Cosella, by the way.
yeah, yeah.
Great presentation. Because most of the time I've been in so many meetups where like developers and not just vibe coders are doing a lot of work in terms of structuring the output on top of the LLM stack, right? So they're taking care of that part themselves, and then they maintain it, they debug it, or they control the life cycle. So with the structured output that you have in here, what would you think is the sort of the best coexistence or the best sort of both worlds where you
Sure.
may let the developers do their thing if they want to structure a part of that output during their workflow, the agent workflow,
Yeah,
vs what can be done like at the lower level when running the
yeah.
model?
That's a really great question. I have seen that in some frameworks, on the agent side or the client side, and I think that both are both adding this type of thing in both locations has value and is important. The value of doing it in vLLM here is like we're doing enforcement at the source, and so it's going to one benefit of adding this is it's going to make your job on the client side much easier. So you're going to be starting with a much cleaner slate in terms of the structure of the response you get back, and and in some cases we can actually improve performance when you use this on the server side. Now, what you can do on the server side, in vLLM is we don't have necessarily as much context and knowledge about any given application. So there's always going to be more complex things you can do on your client side. So that's kind of where I think like layering the two is going to make sense, where let vLLM force the data to be in a valid JSON format for you, but maybe you're going to do more processing, or like the rules you enforce might depend. It might be more like conditional, like, well, if one field was set to this, then you're going to enforce something different set of requirements on the others. Like, I just think there's just going to be more complicated things. That's always best. It's going to be application specific. So I think you need it in both places, but I would always say like let the server side enforce as much of it as possible for you. And I think overall you're going to have a much less error prone system um, uh, by using as much of like what we can enforce for you.
Makes sense.
yeah.
Thanks, Russell. It just
Sure.
reminds me of part of another legacy tech, look, databases, for example. There was always that sort of dichotomy of where to run the procedures, like procedural, the intelligence part. Would it be within the database, within the backend, or within the application? And back in the days, like the people would just say, the closer you to the backend you run your procedures, or like the intelligent part of your application, the better, because it has a better performance. It's straightforward and it's seamless. VS maybe more controlled on the app side, but eventually, like you wouldn't control the performance because you don't have the background of the database or whatever backend it is. So I guess like with vLLM, it's the same thing. A developer doesn't know that much internals around how the model runs within the inference engine.
Cool. That's a good
That makes
analogy.
sense.
Thank you. Yeah.
Thanks. Great. Thanks.
Yeah. Thanks a lot for the thoughtful questions and discussion. I really appreciate it. And yeah, we're at time, so thanks a lot for coming out, coming here, asking questions, engaging, trying to learn more about this. We're really thankful for everyone that's a part of the community and uses vLLM or is interested in it and works on open source. So yeah, thanks for coming. Get involved with the project as you can. Ask us anything in the vLLM Slack or on GitHub. If you're interested in something or want something to be developed, the best way to get that to happen is to ping us and let us know that it's important to you. So, yeah, just thankful to have all you and the community. So, thanks everyone for staying around this long, and have a nice week. Have a lovely time.
Cheers. Thanks, everybody.